Welcome to the fourth lecture on do calculus this time. So last time we saw structural causal models, what we can use them for, how we define them, and some applications in modeling and what choices we can make. For example, having linear equations in the for the equations. So basically, if you remember, we have a set of endogenous variables, which are basically the ones we observe. We have a set of exogenous variables, which are usually noise variables or sometimes unobserved variables. And all of these variables are usually connected via a set of structural equations, which then define how effects propagate through the network. And for the exogenous variables, we then also have a distribution that we assume because we can't observe them, but we assume how they are distributed in their domain. So basically, this could be Gaussian noise or a uniform distribution or whatever. So if we got all of this tuple that defines a structural causal model, this then induces a graph where all our variables are the nodes and the structural equations from the parents to their children define the edges. So just a brief recap, because there was some confusion also from my side. So we define parents, children, ancestors, and descendants. And with children particularly, we mean, or I will use that for the direct children. Okay. So yeah, we saw this plant or watering plant example. Yeah, all the variables are defined to be in the Boolean domain. We have a Bernoulli distribution basically saying, okay, Tom, or our main character, remembers 50% of the time to message his friends that then take care of the plant. For example, the plant is healthy if A or B, or maybe both, care for the plant. Yeah, and this basically the system behaves according to these structural equations. So then we talked about interventions, and interventions basically are the case where we intervene on the system, which means we artificially define or enforce a certain value for a variable. For example, we could say, okay, A is always true or always false. What this corresponds to is that we replace the structural equation with a constant assignment. And this in the graph then means that A is no longer dependent on N. So we also cut the edges to all the parents. So there are some variations. We can do soft interventions. For example, here in the Boolean case, doesn't make not that much sense, but we could shift the values. We could, for example, also say, okay, we take the original structural equation and invert it, or something like this. So yeah, but the main thing is, if you're looking at the graph, hard interventions, and we will mainly talk about them, cut the edges to the parents, the intermediate variable. So then we had a very brief look into causal inference, like what it means, why we want to have it. And basically the main task that we want to solve is usually this query, which means what is the outcome of a particular variable given that we intervene on some other variable. And this is important that we use an intervention here, because what it means is that we decouple it or want to decouple it from any other influence from confounders or variable selection. So we really want to not only observe the system like under conditioning, but we really want to know what it means to change a variable. What are the total effects of like going there and artificially altering the system? Right. And then if we have this kind of thing under some linearity assumptions and so on, we can, for example, define average treatment effects, which is then the probability of like setting x to 1 versus setting x to 0 in Boolean domains, for example, and then observe how much x changes, right? And here there is a lot of assumptions, like if we are in a like continuous domain on the real numbers or whatever, right? We haven't talked about what is if we change x, like leave it here at 0, but change it here to 1, like how it extends beyond like the two cases. So you have to maybe assume that it's a linear continuation, that there are no linear non-linearities and so on in the system, to get a meaningful like semantic of this operator. But for most cases, it's something like, do I want to treat a patient or not? And there, this expression is sufficient. So maybe let's start with the most well-known and maybe also one of the simplest adjustments we can do. Basically, our idea was that we were trying to get rid of this do operator, right, which we first introduced because it gives us all the nice properties, but then try to estimate the effects of this operator from a purely observational setting. And this is important because many times we don't have interventional data, right? We see some sort of data set that someone has collected for us, but it might not have the particular intervention that we want to analyze right at this moment in it. So we probably want to estimate it from observational data, which means we need to transform this query with a set of rules to make that possible. So yeah, the most simple case is that we have a single confounder and that we observe it. Here it's Z, which influences X and Y. And now if we were to go and simply estimate Y, like the influence of X on Y without caring for Z, we would get a biased estimate, right? Because the influence of Z then somehow influences both, and that messes with our regression. So we somehow need to account for it. And this is where the vector criterion comes in. I will simply like show you the definition and we will apply it. And later on, we will have like the exact rules, why it works, how we can derive it. Yeah. So basically, the thing is we want to find an adjustment set, which is just some random set of variables in the graph, distinct from X and Y. And the first thing is for the vector criterion that no node in Z is a descendant of X. So yeah, like X can have no effect on any variable in Z. And that Z blocks every path between X and Y that contains an arrow into X. So yeah, and then we have this sort of formula, which is always the same, and we will see some examples. So back to this very simple graph, we can check our two rules or assumptions that we need to make for this to work. So Z here is not a descendant of X because it's a parent and there is no other path that leads into Z. And here it's also like if we know it's a parent, because of acyclicity, it can't be a descendant, right? Because then we would have a cycle Z to X and X to Z. But so this first rule is fulfilled. And for the second one, we have this vector path, right? We have an arrow into X, but if we condition on Z, this is then simple deseparation. or not deseparation, but set basically blocks this path that goes x, z, y. And also there are no other paths that we need to block. So yeah, then it's kind of easy. We go and we apply this expression we have seen earlier. Basically, we condition x, y on x, and additionally on z. And what we do in the end is that we take the effects of z and marginalize that thing out in the end. So that's basically all. Very, very simple. I think we will do a brief exercise on that in the next lecture. So really, if you have variables like Boolean variables, it's quite easy to see. If you want to do a simple regression without adjusting for z, and once with the adjustment, yeah, we should do that. So right, maybe a bit of a like not much different example, but just to show you how it extends beyond the simple case. So we can have two of these variables, just really simply duplicating the confounder. Now it's the same game again. So we check none of the variables is a descendant of x, both x. So we now have a set of two variables, block all the paths from x to y, and then simply we adjust for both of these variables. So here the one thing, for example, is that this joint distribution, sometimes if there are additional edges or something, you can't draw it apart, but here they are independent, so that makes the computation a bit easier. But again, nothing really special. So maybe have a look at this graph where it becomes a bit more complicated. And again, we want to have the effects of x on y. And we need to find an adjustment set of all the other variables that where no node is a descendant of x, and z blocks every path between x and y that contains an arrow into x. So I don't know, maybe I will leave it as an exercise. Maybe someone has an idea what would be a good adjustment set. Yeah.
Maybe that's C. Z is the descendants. What is
Sorry again.
A, B, and Z and C.
So
everything except for D.
A, B, Z, and C. So all of the above.
Yeah.
Yeah, this would actually be a valid adjustment set. So I just, as a hint, there are adjustment sets and like a lot of adjustment sets and minimal adjustment sets. So some of the variables might not be needed. The main trick here is mainly that we need to condition on set, right? Because it's a confounder. But basically, if we do that, it opens this collider here. So we need to break this additional path via B, A, C, and C, set and C. So yeah, maybe try it out. And yeah.
You say B, Z, and C because the effects of A are already C and B and Z?
Yeah, so I don't want to like spoil the answer, but it's like a two variable adjustment set are the minimum, because they are sufficient to block all the paths.
B and Z.
Yes. So for this, there is this very cool tool, Causality, which has also an online editor or page where you can basically try like go and draw these graphs that we just discussed. And so I blacked those out here, but it basically tells you the minimal adjustment sets that you have. And you can also try and click on a particular variable and then say, well, I want to adjust for it, so that you can also check like which additional variables you can adjust for without like breaking the criterion. Yeah, so this is quite cool if you're unsure or want to like do some exercises, prepare for the exam. I can highly recommend like going there and just playing with some of the graphs or just checking your results. So if there's a backdoor adjustment, there's a front door adjustment, obviously. No, so the main problem is that particularly in economy or like very complex systems, we usually don't observe or don't know all the confounders, right? Like it's very hard to like account and adjust for every confounder there is, and basically to collect enough data, think of everything that is going on in these complex systems. And for this, there is another way. So particularly also if we just don't have the data set is unobserved, so maybe we know it's a confounder, but we just can't adjust for it because we have no data, then we can try to apply the front door criterion, which basically means that we have an intermediate variable on the path of x to y, and we basically use this variable because it's this path x to m and m to y, these pairs are individually not confounded by C. So of course, we again need to make this assumption that m is not confounded, right? So we still need to be sure that our model is correct, but maybe some expert can tell us, okay, I'm sure this m is independent of all the other confounders. But yeah, if we can do that, then we like take the individual paths here and here and basically fuse them together to get the standard or like total effect in the end. So the first thing that we need to check is that we still, again, want to get rid of this do operator, right? And to be able to do this, we need to be sure that there are no open vector paths from x to m. In this scenario, there aren't, because Z confounds x and y, but we don't condition on y, so this collider doesn't become active. So this path is not open. So we can like remove the do operator and basically just condition on it. And for the second part, again, we want to estimate this m conditioned on do y. Again, we need to check that there is no open vector path. But here there is a vector path, right? It goes m, x, z, y, and here we condition on y. But we can block it by conditioning on x. Sorry for the confusion. Definitely it should be the other way around. Yeah, sorry for this. I think it will be correct in the later slides again, but yeah, you're right. This should be y, this should be. Sorry. And thanks for pointing this out. Yeah, it's fine. Okay. At least the last slide where we put everything together. So yeah, we take do x m conditioned on do x, like this first path or part. Then we want to estimate y conditioned on do m, and then we take all the like the paths or the formulas we got before in the individual parts and fuse them together basically. Yeah. So this is the correct formula, which for the first part, we don't need to do anything. We can just replace the do. And for the second part, we need to condition on the x and marginalize it out. And here it's just be careful. So this x and this x are not the same, because here we have that x from the do operator, which is a particular value, or maybe the distribution we want to observe. And this is an intermediate variable, which we only need for the second part to do the adjustment here. So these are not the same. Don't get confused by that. Yeah. But once we have this, we can simply plug it into our favorite library or compute it by hand. And it will then give us the unbiased estimate of the effects of changing x on y for this particular scenario. Yeah, so again, here are the formal criteria. So SAT needs to intercept all the paths between x and y, so all the directed paths in that direction. There cannot be a backdoor path from x to z. It's like, at least for this criterion, it's not allowed. We will see the general case later, but here only these frontal paths is what we are looking for. And again, because we saw in the second part of our derivation, there might be backdoor paths happening from z to y. Like if we want to do this do z onto y, they need to all to be blocked by x, basically. So really, this is the second part, right? Telling us there might be backdoor paths, but we can't block them. Right, and then this actually is the general formula. Of course, it extends if we get like multiple sets or like multiple variables in this set. So the m here as a single variable could be multiple ones. And then we get multiple sums because we need to sum them out for every of these variables. So maybe you remember back the last lecture, or the first lecture, actually, where we talked about, okay, but what can we now do with it? So, for example, the tobacco industry claimed that smoking might not cause cancer, that it's some genetic factors or whatever going on. And here we could, for example, of course, in reality, it's way more complicated, and there might still be a debate of whether your causal model or your graphical model that you're drawing is correct. But for example, you could say, well, I'm not really sure. Okay, we can sequence all the genes by now, but maybe we are not sure we really understand how things work, and maybe we treat them as unobserved, or like we don't know the effects exactly. But maybe we can like measure the depositing of tar in the lungs. And now we have an intermediate factor which we can measure. And we can, I think, all agree on that the deposit of tar, or that tar does not appear because of any like genes or whatever, right? So basically now we have this exact criterion of the frontal criterion where we can estimate some sort of effect of smoking on getting cancer via these intermediate variables, and we are free, or like do not have to find this counter argument where we need to like exclude every possible gene or whatever environmental factor there could be that that could otherwise confound smoking and getting cancer. So yeah, this is a really nice example. Of course, then you can say, well, maybe there are other effects going on and so on, but yeah, at least we are getting rid of all these weird confounders that there might be, and that that people might bring up otherwise. So then it really becomes a discussion by the experts whether this model now really holds, like if there are some intermediate other factors that we didn't observe. But I think you can see a quite strong effect probably from just computing this. So the criterions that we have seen before, front and backdoor, they are somehow sound but not complete, which basically means that if we see some adjustment set that that makes the backdoor criterion identifiable, we know we are computing the right thing, so we know we get an unbiased estimate. Same thing for the front door criterion, although I wrote backdoor again, but so for back and front door, if we find a valid adjustment set, then we know we get an unbiased estimate. But there might be cases where front and backdoor don't give us an unbiased estimate, or at least the conditions for applying it don't hold. But we could still get some sort of estimate that helps us to identify the true causal effect. And this is then basically done via the do calculus, and we will make a brief excursion to that. Right. So this is maybe one of the most important set of rules in causality, because differently from the front and backdoor criterion, these rules are not only sound but complete, which basically means if you find a way to adjust for some variables according to the rules I will show you in a moment, then you are guaranteed that you get an unbiased estimate. And on the opposite, if you don't find, and by that I don't mean that you are not able to find, but you can show that there is no such estimate. If you don't find an adjustment set, then you also know that the formula is not identifiable via observational data, which is quite an important insight, because then it tells you, okay, you need to make some further assumptions. So here there's this one thing where it says, well, the do calculus is for non-parametric models. And what this basically means is that if you, like, we don't assume any functional form on our structural equations, right? Like, as we have seen before, we work with the distributions of the variables and how they, how we adjust for them and whatever, like normal rules of probability. But we didn't assume that there is a linear dependence between variables or something like this, right? And this is the same here. So we don't make any assumptions on the functional form of the equations between variables. But sometimes, and I will show an example later, if we make assumptions on that, we might still be able to identify some effects which are not identifiable in the general case. So this might be important and help us in some cases. So maybe let's jump right into it. And I'm sorry, I mean, these are graphical criterions, but I think the best thing to understanding them is to later apply them and really just have a look at it. What I mean on particular graphs when you apply them. I try to always give some easy to understand interpretation, but at least for the second and third rule, then it's a bit more tricky to figure out when we are able to apply all of these variables, all of these rules and conditions. So basically what all of these rules have in common, that we have sets of variables, x, y, w, and z, or set, and these all can be sets of nodes. Commonly usually x and y, we are interested in a single node, but that doesn't have to be. And additionally, W oftentimes, sometimes also set, can be empty sets. So when we have cases, for example, where we don't need to adjust for things, here it's a bit tricky, for example, because we want to have an independence between y and some sort of variable. Yes, and I think this is a quite easy to understand rule. Basically, what it tells us is under which conditions, if we have such an expression, we can delete observations, which basically means, if this intervention do X makes Y and Z independent in the intervened graph, then we can simply remove it from our equation. So then it has no influence on the probability or distribution we're trying to estimate. So yeah, I think that is quite easy to check. And just a small hint, if you look these things up in the original paper or also in the books Causality or Book of Y, you might find that instead of do X here, they do not use the do operator directly, but they say, okay, we fix the value of X to a particular value. And here we observe the graph where all edges into X are cut, which basically is the do operator in that case. But just hint, don't get confused if you see something else. I think it's an X hat that is used in some of the papers. So then, and this is where this notation maybe makes a bit more sense, because here we are cutting all arrows into X, and here this underscore basically means that we cut all edges that go out of Z. And this is similar to the rule before, but here it's not that we can delete an observation, but here tells you under which conditions we can basically get rid of a do operator. So where we can exchange a do set by a simple set. Yeah, and if you look at the interpretation, or this can basically be done if these two variables become independent in this particular graph. So the cutting edges into set, that is basically again from this do X here, and this expression here basically tells us that we want to find, or can only apply this criterion if there are no vector paths that go into set, or that no, the other way. So yeah, that there are no vector paths that go basically via set, because otherwise it would make a difference if we cut the parents or not. And if it doesn't make a difference, then we can exchange it. So we will see on an example later, but really it can be quite hard to figure out, if you have a graph, okay, which rules do I need to apply? Also, the tricky part here is that sometimes you want to do it in the other direction. So sometimes you want to do an intermediate step and introduce a do operator on some variable, in order to be able to apply some of the other rules later on. So yeah. So, and now the third and final rule, at least there are only 3 of them, is this one, which is now a bit more stronger criterion of the second one, which basically tells us, okay, not only can we remove the do operator on and only condition on set, but we can remove the do set altogether. Like basically we ignore this variable here. Yeah, and this is, again, we need to show independence between X and Z. And now this part here, we do a bit of a weird thing to the graph. Again, we cut all the edges that go into X because we still have this do operator here with do X. But then we also cut all the edges that go into variables that are not ancestors of W. So again, the idea is that we need to make sure if we delete this do operator that there is basically no causal effect traveling through set, and that removing this basically has no effect on the quantity we are trying to derive. So there are basically two cases. Either there is like no causal effect traveling through, or it's not affected, set is not affected by Y, or if it not affected by X, sorry. But if it is affected by X, then at least we have no collider or nothing else. So this effect that goes through set does not reach Y, right? So set cannot be directly be affected or have an arrow into Y, or if it does, like we don't want it to be a parent of any of the W nodes, because this could, if we condition on them, they're still in the conditioning set, right? This could close colliders and also give like open a path that then has an effect on Y. So basically, really, it's a bit tricky to check on the graph, but basically what it means is that if we see that we intervene on a variable and there is no causal effect traveling through that goes from X into Y, then we're fine to remove it. But really, like, stick to, like, this is the intuition, but really stick to this, like, checking this graphical criterion. Yeah, so here again are all the rules. As I said, the first one, it helps us to remove some observational quantities. The second one helps us to remove the do operator and switch to conditioning. And the last one helps us to remove the do operator or a do operator altogether from our estimate. Yeah, so this is the easy derivation of the frontal criterion. So I just put it here because it has some nice mix of applications of the rules. We won't go through it like step by step now, but maybe you can sit down and as an exercise, like check all the individual steps. I'm pretty sure I haven't messed anything up. Because this is basically, if you look into, I think in Causality, I think also in the book of Y, there is this exact derivation. Again, they don't use the do operator, but like fix the values of M and X and so on, but again. So maybe what it also tells you, right, it's not only the rules of do calculus. Of course, all the rules of probability apply. So here in this first step, what we really do is that we still like factorize or decompose this joint distribution or this distribution we have here according to the causal graph, right? So we say, okay, we want to have x conditioned on y conditioned on x and m. And here, because of this confounder, we aren't really sure, like m would block this chain x, m, y. But because of this confounder, we still include the x here because we aren't really sure if it might have some influence on the variable here. And then again, this other part, right? That's easy then. This is where which we had or what we had before. It's the direct effect of of x on y. No, did I mess it up? Oh no, right. This is m on x, right? So this is this first part here. Yeah, but this is really the decomposition of the distribution according to this graph. And here in the very first step, we get this weird or unintuitive, I'd say, application of rule 2, right? Where we introduce a do operator to then proceed further. Here in the third step, we at least do the other way around. Here we remove the x. This is, I think, what we have argued before, like in the initial derivation of the Frontal criterion. Yeah, and then we do, yeah, really just this chain, and I fear there is no like general rule of thumb how to apply all these transforms, right? So sometimes you have to apply some, like introduce a do operator. Here we can then remove this do x and so on. Here again, we apply, like we add this intermediate variable, and it's sadly a thing that you just have to build up some intuition, maybe get a bit lucky, do a bit of a search to find the right formula that in the end gives you the estimand that comes without any do's. But yeah, basically you somehow need to know what you're looking for, like have some intuition how the formula in the end needs to look like, and then try to find a series of applications of rules to arrive there, basically. But don't worry, like we won't ask this in the exam. It's just to show you what can be done. And in the book of Y and so on, there are also other applications which are sometimes easier and also which then instead of do x to do the effect of y, you could also have cases where it's maybe unethical to directly intervene on x, but you still want to get the effect of x on y. So there is also some sort of like conditional adjustment or like to have some other proxy variables that are derived from x and so on, that you then can use to get some information on x, and from that estimate the effect of x on y. And this might or might not still include some do operation and so on, and can all be like derived with the help of do calculus. So as an exercise, and we won't discuss it here, and then maybe in the next lecture or start of next lecture, maybe you can try to derive the vector criterion, and there the hints I can give you, it's much easier, I'd say. It's only, I think, 3 steps that you need to apply. And the first step again is like this, not a do calculus rule, but like decompose this expression according to the graph. And then it's also rules 1 and 2, which might be a bit easier to apply. So this weird rule 3 doesn't play a role here. But yeah, maybe you can give it a try, have a look at it. And of course, you know what should be the result. So maybe you can also try to work your way backwards from knowing the result to getting back to this formula. Although I think both ways are fine. So then as a last part, we now saw a lot of graphs which are identifiable, but there is also a lot of cases where graphs are not identifiable, and this is really taken from the book Causality. Some cases that are not identifiable are, for example, if we have on a path from x to y, if we have some confounding directly from x to any of its children, there's sadly no way of adjusting for that, right? So we have no intermediate factor. We can't condition on the confounder. That's, for example, a scenario that we can never recover from. Like if you see this, yeah, you don't need to search any further. There is no way we are going to adjust for that. In a real scenario, what you will do is then probably think of, okay, is there any way that I maybe get data where I can just control for x, right, to break this confounding error that goes into x? Or maybe can I collect some data on some mediator that is on the path, right? Some variable in between there. Yeah, because otherwise that's a problem.
Would it be if you had a node between x and z, you could do front door adjustment and then
Yeah, exactly, right. That's the thing. So if we have an mediator in between x and z, then we do the front door adjustment and then we're fine again, right? But yeah, like with these graphs as they are drawn here, we have no chance.
Sorry, back to that again.
Yes.
Is that maybe like in practice, could that be framed as a feature engineering problem?
Oh yeah, definitely. So I mean, this is also what you sometimes then see in maybe machine learning or whatever. Like if you're doing all these kinds of adjustments, you need the right data, right? So it might not be that it's not that we can't identify the problem per se, but this is always about which variables have we measured. Do we have enough data to get an unbiased estimate? And if we don't have that, then we need to think of ways, or usually like if we know this graph in advance, we would go to our clinicians or whatever and tell them, hey, I know a graph looks like this. Could you maybe think of a variable that is in between, that is a mediator? Or could you maybe record this confounding factor, right? I mean, that's also a possibility. If we know this factor and we just can adjust for it, then we're also fine. So yeah, this is of course a modeling problem or a general problem if we are just given the data. But of course, we should be smart in advance and try to collect the data in a way that we can estimate these effects. Because from this graph structure, we know in advance if we can estimate them or not. It's not like we need to wait for the data and then be surprised that it's not sufficient or something, right? It's really on the graph structure, not the data itself. But with the graph, it depends on the variables we record.
So if you think about maybe a bit unrelated, but if you think about binary classification using deep learning,
yes,
if you interpret it as trying to find a representation of the data that you're trying to linearly separate it, could you, or has there been research in finding a representation or embedding of the data that
yes,
would give you convenient causal models?
Yeah. So I mean, it's always a bit tricky to talk about causal models in deep learning models, right? To like reason about does my neural net, my, I don't know, diffusion model, does it do vector adjustment internally or whatever, right? Probably not. But what you can do and what has been done before is there are works on causal representation learning and also on like neural causal models, which, for example, then adjust, like try to learn these individual arrows between X and Z, Z and Y, and so on via neural networks. And then if you fit these functions via neural nets, then you can still, on top of it, apply your adjustment and so on, right? So maybe you extract individual features from an image and you have your label Y that you want to like predict or regress, and then you use your neural networks to extract some features, and on top of them or from them, you then do some sort of adjustment to account for biases.
That's that interpreted intervening or even interpreting as well.
Yeah, but I mean that's so yeah, I mean you need to start with something, right? You need to make the assumption, for example, that your neural net truthfully extracts features, for example, that it's not biased, that it really looks what we saw before, right? That it, for classifying horses or like indicating if there's a horse in the image or not, that it really looks at this image content and not at some spurious feature like that's confounding, for example, the image and label. But we will, like right after finishing all of this rather formal stuff on simple graphs, and next time we will do causal discovery, but then we will start on like deep learning or causal and neural methods, and then we will show you criterions under which we can guarantee that our models like learn the right thing, learn disentangled representations, and also how we can make them to regress to unbiased predictions. Yeah. So maybe before we do a short break, just this one case, the graph that was also in the slide before. Here we have a very interesting case where we can identify. So again, we want to identify do X having whatever effect on Y. And it is that we can identify the effects of do X on Z1, so this part. We can identify Z1 on Y, but we cannot, like even with the help of do calculus, identify this whole thing. Because, and this is also not always true, but here the intuition basically is that for X on Z1, we have an empty adjustment set. For Z1 on Y, we need to adjust for Z2. And the problem now is that if we want to do this joint derivation, then basically we can't find a formula that basically simultaneously adjusts and does not adjust for Z1. There will always be some vector path that is open via this variable because they are both confounded here. So in the joint, like because we don't make any assumptions on the relation between these variables, we don't know if, like, if we are looking on the total effect on x of x on y, if this Z1 might not introduce some weird behavior, some non-linearities or whatever that we didn't see when we only look at these individual paths separately. So that's the intuition here. But so last time we saw these linear additive noise models, right? And these help us here, because what we now can do with the help of do calculus, we can identify this path, and if we have it, we maybe have an ATE or whatever, we can identify this, the factor, right? So what we are doing now is we are saying, well, this is not like random probability distribution, but this is a linear equation. So if I increase x, Z1 will increase by this alpha or whatever. So once we have identified this, we set some sort of alpha and fix it there. We do the same for the second part, Z1 to y, and also get other alpha, let's say a beta here. And then basically we just can chain this alpha and beta together and know the full causal effect, right? So that becomes then very easy if we can make some assumptions of this underlying process of this structural equation. And also it doesn't have to be a linear equation, right? It can be any functional, any functional form basically that we are able to regress the parameters for from our data. Then it's really just like looking at all the paths from x into y and just chaining all the paths or all the edges along the way together. So yeah, then maybe do a brief break till 11, and then we finish with the whole causal hierarchy. Okay, so maybe let's continue with this last, maybe also brief part, which basically is the whole causal hierarchy. And I think you have seen it before in the first lecture, right, where it was this doing, intervening, and then reasoning about counterfactuals. And now with the tools that we have, maybe we can approach it a bit in a more formal way and try to really see why we have these individual steps, why they are distinct. Yeah, and maybe really start with the most simple insight or thing we have seen right before the break, which basically is that oftentimes we want to estimate queries that involve the do operator, and our goal most of the time is to transform them into queries or estimates that no longer contain any do expression. But for some of these, we just were not able to transform them in something without the do. And basically what this means is that there is a distinct class of queries which does not live on the observational level, so to say. So we can't reduce it to observational only expressions, and they basically form a distinct class. And this is what at least is formally meant with having a different rank, or like being a different class, that for some of the interventional queries we can't answer them with observations, or can't transform them in the way. Then the next thing is if we consider both of these classes, right? So observations and interventions, what they usually do is they give us some probability about the future outcome. So what would happen on average if I prescribe this medicine to a patient? What will happen if I increase the price of a particular product, and so on. So basically, what they do, right? They always reason about average effects on some sort of population, and this population is basically what we define via the noise variables in our structural causal models, right? So there we make these assumptions, how are our latent factors distributed, what kind of noise goes into our system, and then for the average treatment effect and so on, we basically like average or marginalize, not marginalize, but average these effects out. So yeah, that's a thing if we want to make predictions about like general effects, what will happen if we change something in the future, what is the average probability of something happening. But sometimes, and I mean, some people argue at least that what makes humans or other animals also intelligent could be the ability to retrospectively reason about individual outcomes or particular scenario. So basically to think about counterfactuals, which means we take a particular scenario and reason about what would have happened if I had done something different, if I had intervened on that particular variable. Basically, what this means is we reason not only or not about some average outcome or whatever, but for that particular scenario, all the noises are fixed, right? We might not know them, but we know, okay, I don't know, the virus level in my body was at this exact quantity. And if I had taken the medicine, maybe I wouldn't have got sick or something like this. So what we will show again, there are formal proof, but they are very like intricate, and we will stay on the like intuition level here. But basically, what is the difference is that interventional queries reason about like average effects, and counterfactuals then form this third level on this ladder of causality, which basically do an additional step that reasons about the unobserved noise. And I will just show you maybe some examples which hopefully will make this more clear. So yeah, again, this is what we've talked about before. So observational really is how many people that go to parties catch a flu, right? So this is a conditioning, like maybe there is some confounding between like going to a party or being open to go there and like immune system, don't ask me, but so this is classical conditioning. Then what if we order people to join a party? So if your professor or boss says, okay, everyone needs to show up at the company party, then we have a do operation. It's no longer like conditioning according to some random factors, but we know or we explicitly enforce that policy. And in the counterfactual, it's would John have caught a flu if he didn't go to the party, which basically first implies that he went to the party. So we have some sort of evidence, and we don't reason about some group of people or whatever that might be here before in our noise distribution, but we reason about a particular individual, for which we want to know the counterfactual outcome. Yeah. So we've said all of this, many similar questions. What if I learned for the exam? What if I had smoked not smoked in the past? Or what if I had smoked in the past? And yeah, really, it's always about individuals. So maybe because we had a lot of dry stuff on graphs and whatever, I think there's a really nice way to show this in images. So let's say you do a series of photographs of dogs or corgis, and basically on the observational level, you get a data set from your photographer, and he basically tells you, okay, here are all the images, and you just see what you have observed, what dogs you could photograph, maybe in a park or whatever. So, and now you're wondering maybe about the effect of the do operator for these kinds of images that you got. So on the interventional level, things would have played out differently, right? You go back to your photograph and say, well, actually, for my machine learning model, I need to have, I want to have images with dogs which have an apple in front of them. And what will happen then? The photographer will go back and he will record a new set of images, like he will sample a new set of data points, if you want to phrase it like that. And for every of these new samples, he will like basically record it with an apple in front of the dog or the corgi. So this is the interventional level. We don't fix the noise. We do the intervention, but we maybe record different dogs, different sets of images. For the counterfactual, what we will do is we will imagine what would have happened to our original data set if we had put an apple in front of the dog. And this is now different, right? Because here the pose is different. It's also different dog at all, and so on. The background is different, and so on. And here it's not like that. So the whole image is the same, except for the intervention we did. And let's say, okay, you see the ground maybe changed slightly, which is because of our image editing, but maybe like putting an apple there had some more effect. Maybe it casts a shadow and so on. So we will observe the intervention. We will think about all the downstream effects that our interventions also had on this model. But like everything that was not affected by this intervention will stay the same. And here, because of image editing and so on, we can like at least imagine how this image would have looked like. But the problem is that in reality, there is no chance to get an image of both. We can only either record this image or this. So it's impossible to have the observational and counterfactual. I mean, it's in the word counterfact that we have both of these images recorded in our data set. So of course you can make a lot of assumptions on like regularity or continuity of the space, right? We could say, okay, we might be able to record two images very close to each other where the dog basically doesn't move, right? So this is then assumes, okay, the noise variables don't change too much. Like this is the image recorded 5 seconds later or whatever. And and so on. But like still, it's not a perfect counterfactual. Still, we make some assumptions and some things in the background, maybe like there's a light breeze of wind and the grass will look slightly different or something like this. So basically, we can't have them both. But of course, and I mean that's the tricky part, because we still want to reason about this quantity, and people often reason about this. So in court, or if you are making an argument, right, you want to attribute responsibility, then it's very important that you can argue, okay, if we had followed my plan, then we would not like be stuck in traffic or whatever, right? So it's still important to be able to make these kinds of inferences, although we will never see or directly be able to compare both data points.
What if you're collecting data from a simulated environment?
Oh yeah, sure. I mean that, and that's something where because we talked about collapse of these causal levels. Exactly. There are scenarios where it is possible, but it's usually some simulated environment, some very highly controlled environment, and practitioners, like if you tell them I can have observational and counterfactual data, they will like very strongly argue against that. But yeah, I mean, for making predictions and so on, it's super important that we identify conditions under which we can make these inferences and compare this. And this is actually all the case, or the reason why we do randomized control trials and so on, right? Because they basically break certain links from the noise variables and let us control for the noise to replicate the data, or at least let us then reason about the counterfactuals. Yeah. So yeah, what sometimes is done in, for example, medical studies or whatever, is that you do some, okay, this is then also statistical matching and so on, but oftentimes you do some sort of propensity score matching and so on, where you like find, for example, patients that like are very similar in their features, like in their weight or height or whatever. And then you randomize things where you treat one of them and do not treat the other one. So you try to like have two patients, make them as similar as possible, and then see the like divergence of effects from treating one versus not treating the other. Sure, there's a lot of like ethical questions involved and so on. But yeah, there are ways to get around this, and yeah, of course, not all hope is lost there. So, but maybe having looked at all of these nice pictures and also maybe having discussed what this means, there is a very simple, or there's an actual algorithm or step-by-step procedure to compute counterfactuals. And basically what this task is to, yeah, being given a model, given some distribution. So this is your structural causal model, and just because we will like modify this, we note the exogenous distribution outside. We want to compute a counterfactual P of EA given E. And what this notation means, there are also others, depends on the author, but this means that we want to find the probability of some outcome A, given that we intervened, some outcome B, given that we intervened on A under some set of observations or some set of evidence E that we know that happened. So basically, to trace it back to what we said before, the first thing that we want to do is we don't want to do or reason about some average random scenario, but we want to take the evidence, the observations that we have or that we were given, to reason about the most likely state of the exogenous variables. So basically, we take the evidence and say, oh, if, I don't know, John went to the party and got sick, we might want to infer some property or likely value of his immune system or whatever. Then the next step, so this is basically inferring all the noise in the actual world. The next thing that we do is we apply our operation, our intervention now to the graph. So before, this is the unintervened graph, right? This is like purely statistical inference. We infer U given E. Now we do the interventions, and I think we've seen that before. And now we take our updated model with the intervention, with the updated evidence, and from that compute the outcome or the probability of the outcome of B. And these kinds of pairs, the causal model or graph that we have, and the probability distribution or like exact values of U is sometimes called a causal world. So that if you like have different U's, I mean, this is then sometimes up to debate or how you infer this U's, then you can basically reason about different like factual or counterfactual causal worlds. So yeah, it's this three-step procedure, and maybe just let's do a simple example, I'd say. I modified the scenario slightly. So this time, Tom always messages either one of his friends. It just decides for one of them. So either he messages friend A and he takes care of the plant, or he messages friend B, who takes care of the plant. But like it's either A or B, not both together. And let's assume we saw friend A watering the plant yesterday, and we want to know what would have happened if we prevented A from watering. Maybe we like went there, got him into a discussion, and he forgot to water the plant, or we just took away the water the can from him. So yeah, this is the scenario and the question we want to answer. And this is a counterfactual question, right? So the event already happened. We know the plant is healthy, and we want to know, okay, but what would have happened if it were different, if things would have played differently. So basically, the first step is this abduction step, where we take our evidence. We saw friend A watering the plant, and reason about what does this mean for our U. Let's say this, okay, I drew it with a full line, but maybe this is unobserved for some reason. So given A, we know that M was true, we know that U was true. So this is basically, we know this is true, and we trace back through the structural equations, right, which basically just copy the value of A, and then U was also or M is the same value as U, so we can infer that U was true in this setting. Then we intervene, right? We want to know, okay, but what would have happened if A didn't water the plant? So we do an intervention here. We cut this this edge. Sometimes I'm not sure if I've mentioned this. Sometimes interventions are also like marked with some sort of hammer. So then we just remove this edge and know it's like put this hammer here to say, okay, it's not the normal observational state of the graph. Yeah, so this is quite simple, exchanging the equation again. And yeah, step 3, unfortunately, then gives us the counterfactual outcome, or fortunately, because it didn't happen. So we take our model, we have the intervention here, we know our U is false, and we run the whole system again. And what will happen is U is false, therefore M will be false. This edge doesn't exist anymore. A will stay false because we intervene on it. B will be false because it's the opposite of B. Oh, does it say? Yeah, right, because M was true, B will be false. So all A is false, B is false, and the plant is no longer healthy, or would have not been healthy. So this is a quite nice scenario where we have deterministic equations. This seamlessly translates to scenarios where we maybe have some noise in the equations. The only difference then is that we, like here, don't have like U is true or false, like with 100% certainty, but then we could have some sort of probability distribution, right? So it could then say, well, it's maybe 20% true, 80% false, or something like this. And then we still do all the 3 steps, abduction, action, prediction again, and find the outcome or outcome distribution in that case. So for this last part, just a very nice intuition, because here in the previous part, we did infer some U, then we did some interventions on the graph, then we did rerun it again. There is this representation called twin networks, which basically duplicates the graph and connects these 2 graphs via the exogenous variables U. And this is maybe a bit nicer because you can do all these steps within a single model, within a single graph, without like doing this step simultaneously, right? So you apply your evidence on the left, which is the factual world that you observed. You infer the U's here, and then from there you go to the right side, the counterfactual world, where you apply the intervention and just down propagate your U values to the quantity that you care about. So yeah, this is sometimes a bit nicer. Again, yeah, so last minutes. We talked about interventional and observational collapse, right? Which basically tells us that sometimes under the rules of do calculus, we can transfer these quantities into each other. And then, because the question came up before, there's also a collapse between interventional and counterfactual ranks. And basically, if you think about it, it's that the interventional case, it only does steps 2 and 3 of the counterfactual algorithm, right? It only applies the intervention and then reasons about the outcome. But it doesn't do this first step where we like infer or update the probabilities of U. So this basically makes it different from counterfactuals. But on the other side, if we have evidence that does not influence our belief in U, or that is like irrelevant for the outcome of what we care about, then these steps are the same, right? Like if the evidence doesn't matter for the exogenous variables that in the end influence our Y that we care about, then we don't need it. Then it's the same as doing interventional inference. And again, what we also can do if we have interventions, because here, right? If we have enough interventions here so that we cut all the edges that go into U, then of course this results on D here will also be independent of U, right? So then there will also be no difference between the interventional case and the counterfactual case, because again, we cut all the influence from of U on our target variable. So in these cases, also the interventional case and the counterfactual one collapse. And basically, if you think about simulation or simulating environments, that could be something, right, where you say, okay, maybe I do not intervene, but I either control you, or I can control the environment so closely and set variables again with such a precision that the outcome basically is the same as, like, there is no difference between interventions and counterfactuals. Because I observe everything, I control the whole environment. Yes. And that's it. Are there any questions? If not, then thank you and see you next week.